Okay, so the materials property about the failure. So in this chapter, we're gonna uh, discuss how do cracks that lead to failure form, and how is fracture resistance quantified, and how do the fracture resistance of the different materials classes compare, and how do we estimate the stress to failure, and how do loading rates and loading history and temperature affect the failure behavior of materials. So here are some examples here. So when we look at the ship broken, so when you look at this picture, so what's your image in your mind and what's your thought? What kind of stress or loading to make it fail? Okay, so you can think of, okay, when we look at the failure situation, no matter what kind of a component or mechanical part is, so we can estimate what kind of force or what kind of stress to fracture. Okay, so for the case, the ship is due to the cyclic loading from waves, probably, and the second picture shows the chip for wire bonding. Okay, the chip wire bonding to the PCB, the printed circuit board. So mostly the failure inside the chips is due to the thermal cycle. Okay, the thermal cycle, and the thermal cycle triggered this called the thermal mismatch between the chips and the printed circuit board. Okay, and this thermal mismatch is due to the different coefficients of thermal expansion, right? So when you have the thermal loading, and a different layer of materials has its own coefficients of thermal expansion, right? And this thermal mismatch causes this kind of failure, the chip's failure. And the third picture shows the hip implant. Okay, and the failure is caused by the cyclic loading from walking or from some exercise. Okay, from some exercise. Okay, so when you look at a picture, or when you focus on the cases, the failure case, you need have this ability to estimate what kind of mode, okay, or what kind of situation to fracture this component or parts. Okay, so there's some pictures shows the crack form. Okay, we can look at those crack. Oh, well, like this crack is obviously on the surface. We can see it by our bare eye, right? And some cracks, well, maybe is from interior crack, but not from the surface. Okay, in this case, we might observe it under a microscope. Okay, under a microscope. Okay. Okay, so the crack propagation, the crack form. So initially we assume there's a initial sharp crack form, right? And when we keep applying the force, the crack will propagate. Okay, the crack will propagate when we apply a force. Okay, when we apply a force like this, the crack will propagate. Okay, in this direction. So when we have an initial sharp crack and when we keep applying the force or stress, this crack will propagate. Okay, initially it's gonna plant a crack. That means the sharp core, the sharp tips will become a planted tips. Okay, and in this case, if we keep applying the stress, the second phase, the second fracture phase will form. Okay, so the second fracture phase will form another sharp crack tip. Okay, so when this the tips is planted and we keep applying the stress, and the tearing begins, and the second a fracture phase form. Okay, therefore the crack will keep propagating, Okay, so to be a mechanical or material science engineer, we need this ability to tell what kind of fracture it is. For example, from this from the fracture surface or from its failure situation. Okay, so for example, when we look at this picture, figure A, right? Well, when we see this case, okay, so you can estimate this material is ductile. It's ductile fracture, which is accompanied by significant plaque deformation. That means numerous dislocations accumulated. Okay, and when you look at this picture, you can estimate it might brittle fracture. Okay, my brittle fracture. Okay, maybe have some little or no plastic deformation. Okay, and this brittle fracture always causes a catastrophic disaster because there's no plastic deformation. Okay, so you can compare the difference between the ductile and fracture, ductile or brittle fracture, right? You can compare between them. You see, for the brittle fracture, in this kind of this fracture situation, is always like the pieces. It will fracture in pieces. Okay, and for the ductile fracture, it's always have some due to its plastic deformation. So it's a whole parts body might be still keep in a shape, and some crack just keep propagating. Therefore, for ductile fracture, usually would not cause a catastrophic disaster due to this plastic deformation, right? Okay. So it's a real case from some a bicycle. So if you can see those fracture on the surface, if you can see your bike or some machine parts have some cracks on the surface, I would suggest you just leave it. Okay, just leave it. Okay. Okay, so we apply a tensile test of a materials. From its fracture surface, we can tell or we can estimate its fracture mode or fracture behavior. Its fracture behavior. Okay, and a ductile fracture is usually more desirable than brittle. Okay, than brittle. And those ductile behavior provide a warning before fracture. Okay, and otherwise like brittle fracture is without any warning before fracture, right? So you are gonna fail to cause a catastrophic disaster. Therefore, we cannot use some brittle materials to build up a house, to build up a car, to build up any vehicles, right? Because if a car accident happens, your car or your vehicles will become pieces. Okay, will become pieces. Even the body, the driver will become pieces. Okay. So let's compare the idea and the real materials. So usually the real materials, the real materials have more we say the flaws or void or defect inside. Therefore, their strengths, or their Young's modulus, whatever, always is always lower than that of the ideal materials. Okay, so the Da Vinci observed that the longer while, the smaller load for the smaller load for failure. So the Da Vinci discovered this situation 5 years ago. So what are the reasons for this situation? I mean, the longer wire, the smaller load for failure. That's mean easy to fail, easy to fail. So if we have a longer wire or we have more materials, that means we have the more possibility to have higher density of flaws or higher density of crack or higher density of the defects inside the materials. And this defect or this crack, these flaws or are different from those such as the point defect that we already mentioned previously. That's totally different. Okay, in this case, the flaws, I mean the flaws are macroscopic point of view, but from this those defects we mentioned previously, like point defect, as the microscopic point of view. Okay, that's a totally different kind of scope. Okay, for failure. Okay, for the flaws are mostly are always bad, right? But for those point defect, while mostly are good for strengthening those materials, right? Okay. Therefore, if we have a longer wire, that means we have more flaws inside these materials, even we use the same materials. Okay. Okay. So if we look at this component like this, they have an inner flaw inside or a flaw on the surface. When we apply stress, what's going to happen? The stress will concentrated at the crack tip. Okay, or here. Okay, so if we have this stress versus position, you see the stress concentrated at the crack tip, the crack tip. Okay. So the Griffiths provide the theory, the fracture of theory that mentions the maximum stress concentrated, the maximum stress. Okay, concentrated at the crack tip, okay, is the geometric dependence. Okay, it's geometric dependence. So it's related to the applied stress and the crack length or the crack size and the radius of curvature of the crack tip, okay, equals to KT times the applied stress. Okay, so what is the definition of KT? It's a stress concentration vector, okay, which is related, which is geometric dependence. Okay, geometric dependence. Okay, so from this equation, you can observe that if we have a very sharp crack tip, so how this stress concentrated, how do this stress concentrated around this crack tip? If we have a very sharp tip, right? Sharp tip, that means it's smaller, right? So we're gonna get a higher stress concentrated around the crack tip, okay? So if we can compare, we can look at the stress distributed with the distance or with the position. Okay, we can figure out that the if the stress, if the crack is on its surface, okay, it's on the surface, okay, and we still apply a stress, okay, apply stress. Okay, so this line, this red line shows the stress distributed. Right, this line shows the stress distribution. Of course, the stress the maximum stress still at the crack tip. Okay, and the stress concentrated at the crack tip will keep reducing. At certain location, it shows the Ry from the crack tip, the distance from the crack tip to certain point defined as Ry. What's this Ry? What's the definition of the Ry? That's mean if the position beyond this, the position between the crack tip and the Ry, the plastic formation occur within this distance, okay, or within these two positions, okay, and the position is close to the center, close to the center of the sample. This deformation belongs to elastic behavior. Okay, belongs to elastic behavior. Okay, to the box center. Okay, and the stress close to the crack tip belongs to the plastic deformation within Ry. Okay, within Ry. Okay. So we can calculate the Ry equals, which is the equals to the sigma naught square times I divided by 2 sigma y square. Okay, and we already know that the maximum stress concentrated at the crack tip is a geometric dependence vector, right? And we define this the constant Kt is a ratio of the maximum stress concentrated at the crack tip divided by the applied stress. Therefore, we can figure out that when we have a crack or flaws inside a component or on its surface, we want to reduce the stress concentration vector, right? This Kt, right? Kt is a stress concentration vector. Okay, from the design point of view, we also want to reduce the Kt. Okay, we want to reduce the Kt. Okay. So from the design cases, we can look at the, for example, we have the parts like this. It's a T-shaped component, and the width of the bottom is W, and the width of the head is H. And we have these fillets. We have the fillets. Okay, 2 fillets. Okay, and this radius is R. So when we look at the figure right here, if the H is fixed, for example, the H is fixed, right? So if the R over H value is approaching to left, what's that mean? That's mean sharper fillet radius, right? Sharper fillet radius. Okay, and the Y, the definition of Y is a stress concentration vector. Okay, stress concentration vector. So if we fix the ratio of W over H, for example, this is the first line, the second curve, the third curve, right? So we can figure out that if the sharper failure radius, we get the higher stress concentration, right? We get the higher stress concentration. Okay. Okay. Therefore, for the design point of view, for the machine design point of view, we always want to avoid this kind of sharp tip or sharp corner, because those stress always concentrated at sharp corner, and to cause the failure in the first initially. Okay, so therefore the initial failure is always at the sharp corner. Okay. So the criteria for crack propagation. So how to define the shock to start, to begin, to propagate? Okay, if the maximum stress, we already mentioned that the maximum stress is located at the crack tip, right? So when the maximum stress is higher than the critical stress, okay, this crack will begin to propagate. Will begin to propagate. And the critical stress is the materials dependent. Okay, it's materials dependent. Okay, you have a Young's modulus and the crack size. Okay, and here is a vector, it's gamma s, which is the what? Which is specific surface energy. So what is a specific surface energy? Well, I will just provide you some a concept. Okay, in this course, we don't have to dip into this detail of specific surface energy, but we need some concept, fundamental concept of specific surface energy. Okay, and for ductile materials, we can replace this specific energy with gamma S and P. Okay, because for the ductile materials, usually have the plastic deformation, right? Plastic deformation. Okay, so what is gamma S? What is the specific surface energy in a wall? Is that the energy gamma S is required to open two fracture surfaces. Okay, so we already see this figure previously, right? So for a component or for sample, you already have a crack formed and has a very sharp crack tip. Okay, and then we apply stress. And the tip start to propagate. The tip will be planted initially, right? From sharp to planted, right? If we still keep applying the stress, that means the second surface form. Okay, therefore the second surface, the energy to open the second surface is defined as the specific surface energy. Okay. Okay, so in this case, its case shows we have a cantilever beam and we have a crack on the surface, and we apply a load. And we release it. We can open the first fracture surface. Okay, and then we reload it again, and release it again, and we can open its second surface. Okay, we can open its second surface. Okay, and the area under the stress and strain, or we say the load and displacement curve, is energy, right? It's energy. Therefore, the energy to open two surfaces, to open the second crack surface, is defined as the specific surface energy. Okay. So let's define. Let's define what is the fracture mechanics is. So what is fracture mechanics is? It's just a discipline concerned with the behavior of materials containing cracks and other faults. So for those mechanics you learn, such as like the materials mechanics, we always assume that no matter what kind of materials it are, there's no flaw or no cracks inside. But for the fracture mechanics, we have to concern the cracks or flaws already inside the materials. Okay, if there's crack already inside the materials or on its surface, and we keep applying the stress, what kind of failure situation it's going to be. So that's the fracture mechanics have to concern. Okay, concern. So let's look at some parameters such as the fracture toughness, which is the measurement of the ability of the materials with flaw to withstand applied load. Okay, so we already mentioned the toughness, right? We look at the stress and strain curve, and the area under the stress and strain curve is defined as the toughness. And the fracture toughness is that this material already has the flaw inside. If the materials already have a flaw inside, and what's the ability of the materials with flaw to withstand applied loads? Okay, therefore for the fracture toughness, that the materials is not perfect, it's not ideal, right? It's not ideal. Okay. Therefore, we provide the factor is called the stress intensity factor to define the fracture toughness. To define a fracture toughness. Okay, so the stress intensity factor is, we use K to define the stress intensity factor. Okay, use chi equals to F, which is a geometric vector, or some references will use Y instead of F, and the sigma is the applied stress, and A is the flaw or crack size. Okay, so we use this chi to define the fracture toughness. And the critical stress intensity factor is Kc, critical, equals to K required for crack to propagate. Okay, so as I mentioned that the F or Y is a geometric vector, right? Therefore, if the sample is infinite plates and internal crack, the situation is belongs to internal crack. In this case, the geometric vector equals to 1. Okay, and if the plate is semi-infinity and the single edge, the crack is on a single edge on the surface. In this case, the geometric vector is 1.12. Okay, it's 1.12. Well, therefore, we say the Y or F is geometric vector. Okay, it's geometric vector. Okay, so it's two cases, two 3D cases. If the crack is on the edge or on the surface, and it's a semi-infinite plate, so the geometric factor equals to 1.12. Okay, the second case. Okay, and if this sample is infinite plate, that's mean in this direction is infinite, in this direction, and in this direction, infinite, and the crack is internal. It's internal crack, and the geometric is defined to be 1. Okay, defined to be 1. Okay, so let's look at the fracture mode. Let's look at the fracture mode. We have 3 types of fracture mode. Okay, the first one is called the opening. Okay, that means we have the crack here. This is our crack, right? This is the crack tip, and applied stress is to open the crack. Okay. Okay. Therefore, the stress, the fracture toughness of fracture mode 1 is defined as the K1C. Okay, K1C. That's mean the fracture toughness in the fracture mode 1. Opening is K1C. For the mode 2 is sliding, right? It's K2C. Okay, K2C. Okay, it's sliding. This is still the crack here. And the failure mode is sliding. Okay, sliding. Okay, and for the failure mode 3 is tearing, right? It's still a crack here, and we apply a shear to tear this crack tip. Okay, so in this expression, K is the fracture toughness, which is a material's property. Is a measurement of a material's resistance to break the fracture when crack is present. That means the crack is already inside material. Okay, and this fractal toughness is correlated to the thickness. Okay, and for this for thick sample, the fracture toughness is dominated by the K1C. Okay, K1C. Okay, the K1C. Okay. Well, what is the plane stress and plane strain? I think those ideas will be given in the course is called the materials mechanics. Okay, you just have to know that for the thinner plate, which belongs to the ductile behavior. Okay, ductile fracture behavior, and when these the thickness of the sample getting thicker, and the fracture mode 1 dominates its fracture behavior. Okay, dominate the fracture behavior. Okay. Okay, therefore we can realize that for the mode 1, right? Mode 1. What is mode 1? Opening, right? We open the crack. We apply a stress to open the crack. Okay, and it's K equals to K1C because mode 1. Okay, and the critical stress, critical fracture toughness. Okay, and then we can calculate its critical stress. Okay, we can calculate its critical stress. Okay, from this. Right, and we already mentioned that the K1C, the fracture toughness, is material property, right? It's material property. Therefore, if we know the crack size, we can calculate this critical stress. Okay, we can calculate the critical stress. Okay, let's compare the fracture toughness range. Okay, so the same, we have the 4 types of materials. One is the metal, ceramics, plastic, and the composites. Okay, so from this table, you can figure out that the ceramics and polymers have the lower fracture toughness, right? And the metal and the composite have the higher fracture toughness. And you can see that the range, fracture range. Okay, composite has the highest range of fracture toughness. So why? So what's the reason why? That's because the composite is artificial manufacturing. Okay, that's mean the composite is made of by humans. It's not nature. It's not nature material. Therefore, we can adjust its composition between 2 or 3 different materials. Right? For example, we can have higher ratio of glass fiber in epoxy. Right? If we have a higher glass fiber, that means what? So just one question: if we have a higher content of glass fiber in epoxy, its fracture toughness K1C will reduce or increase, and why? And why? Of course, if we have a higher content, we have a higher amount of glass fiber in epoxy, we'll reduce the fracture toughness. Okay, we'll reduce the fracture toughness. So you have to remind the definition of fracture toughness, okay, which is the toughness of the materials that has the initial crack already inside, right? So you can imagine that the glassy fiber will reduce the fracture toughness of a composite, right? Because the glass fiber belongs to ceramics. So from this figure, you will find out that the ceramics always have the lower fracture toughness. Okay, lower fracture toughness. Therefore, if some void or some flaws or some crack inside a ceramic, and if you keep applying the stress, what's going to happen? You will destroy or you will fracture immediately or catastrophically because there's no plastic deformation, right, within ceramics. Okay. Okay, so the ability of the materials to resist crack growth depends on many factors. For example, that's already mentioned that the longer flaws reduce the perimeter stress, right? Of course, of a higher crack size, crack length reduce the permitted stress. Okay, and ductile materials has higher fracture toughness, and the thicker samples have lower fracture toughness. We already mentioned that for the thicker sample, that the K1C dominate its fracture mode. Okay, and increase the rate of load application reduce the fracture toughness. So what's that mean? So you can think of if we have a tensile test, okay, to put out a metal, and this metal already has a crack inside. So if we just put it quickly, or we just put it slowly, very slowly, which rate will reduce the fracture toughness? Of course, the faster, right? The faster rate of loading or pulling or just tensile test. Okay, so if we apply the higher rate of loading for tensile test, that will reduce the fracture toughness. That means the materials will be opened quickly. Okay, that means the crack will be opened, or the crack will propagate very fast, very fast. Okay, and the fracture toughness is related to the temperature. Okay, so increase the temperature increases the fracture toughness. That means this materials maybe will recrystallize, or its grain will regrows due to this this elevated temperature, right? So when the grain regrows and or its recrystallize occurs, and those will increase its fracture toughness. Okay, such as we anneal a materials will increase its toughness and the fracture toughness. Okay. And the smaller grain size increases fracture toughness. We already mentioned that the similar idea. The smaller grain size has the longer grain boundary, right? And those longer grain boundary or smaller sizes increases fracture toughness. Okay, increase the fracture toughness. Especially at the crack tip, you can think of this way. If a smaller grain size, what's that mean at the crack tip? What's that mean? That means this materials will has higher ductility, okay, higher ductility, or it's has more dislocations. It's more dislocations. So you can imagine that the crack tip, at the crack tip, the atom will bond it together, right? And if we have a smaller grain size, what's that mean? What's that mean? That means we have the higher possibility to take apart these atoms, right? Take apart these atoms to increase the fracture toughness. Okay, and in some ceramic, stress-induced transformation causes increase the fracture toughness. Okay, so I show you a figure about this. It's called the stress-induced transformation. For example, we have a BCC structure initially, and when this structure and these materials withstand a stress to transform its crystal structure from FCC to BCC. Okay, so in this case, it might have a shear stress like this, right? We will apply a shear stress. Okay, so it will transform from FCC to HCP. Okay, so if we want to its recover, just heat it up, just apply, okay, a higher temperature, okay, to recover, okay, its structure. Okay, therefore the stress-induced transformation is reversible by temperature. However, for the plastic deformation by slip that we already mentioned, right? By slip, we apply stress. We apply stress and its atom arrange change. Okay, and the dislocation form. And in this case, if we just hit it, it will not, recover to its original structure, crystal structure. Okay, in this case, it's called the stress-induced transformation. Okay, and this stress-induced transformation will increase the fracture toughness. Okay, that means have the higher ability or higher resistance to the fracture. Okay. So the importance of fracture mechanics, what kind of importance is, for example, like the material selection, right? What kind of materials? Because we already mentioned that the fracture toughness is a material's property, right? It's a material's property. So it must correlate it to material selection. So if we know the maximum size of a flaw, we already know the maximum size A of a flaw in the materials and the magnitude of the applied stress, and we can select the materials with enough fracture toughness to prevent crack growth or to prevent the crack propagation, right? And for the machine design point of view, if we already know the maximum flaw size of the materials, we can design a component such that the maximum stress on the component never exceeds fracture toughness. Okay? So let's look at the example of the design against the crack growth of the wing. Okay, I will show this example later. So for the crack growth condition, as if its fracture toughness K is greater than what? The critical fracture toughness. Right, we already mentioned here. Let's show you. Oh, stress. Okay, we already mentioned here, right? Remember that we use the stress intensity factor to define the fracture toughness. Okay. Therefore, when the K, the stress intensity factor, is greater than the critical critical fracture toughness, and the crack will start to grow, or the crack will start to propagate. Okay, so we have two scenarios can compare with. The first one is the maximum floor size dictates the design stress. Okay, so we have to know this the maximum floor size, right? We know the maximum floor size, and y is a geometric vector, right? Geometric vector. Okay, so we can design this stress. So we can plot the figure of the stress versus what? The floor size. The floor size. Okay. If the component design within this range, that means component will not fracture, right? Will not fracture. Okay, if we have a floor size and the stress at this point, right? If we know this this floor size is right here, and we calculate as design stress as in the fracture regime. That's what's that mean? That means this design fail. This design fail. Okay. Okay. So the scenario 2 is the stress. This design stress dictates the maximum floor size. That means we design this stress, right? The stress, and we can figure out the maximum floor size. Okay, right? The similar plot like this, where the maximum floor size and applied stress. Okay, therefore, if we know this design stress and we can calculate its floor size, maximum floor size. Okay, if this design is within this range, that means this design will be fine, will be okay. Okay. So let's look at the some example about the aircraft wing. And we already mentioned that the fracture toughness K1C is a materials property, right? And we have to consider two design for design A and B. For design A, is that the largest floor size is 9 millimeter. Wow, it's almost 1 centimeter. And the failure stress is 122 megapar. Okay, and for design B, we use the same materials. Okay, therefore this fracture toughness is the same, right? It's the same, and the largest floor is about 4 millimeter. And what its failure stress is? What is failure stress? Okay, so we already know the critical stress, right? The critical stress. So equals to fracture toughness divided by the geometric vector square root pi times the floor size, the maximum floor size, right? So Y and the K1C are the same for both design, right? Because we use the same materials. And same aside the fracture mode. Therefore, the Y and the K1C are the same. Okay, therefore we can know that the K1C divided by Y times square root of pi of these two design is the same. It's constant. Okay, it's constant. Okay, it's constant. Okay, is that clear? It's constant. Okay, therefore we can compare these two design. Okay, for design A is that we already know the critical failure stress is 120 megapar, right? And we know as the largest floor size, right, equal to a constant. right? So the design B, we already know we have to know it's a failure stress, right? And we already know its largest flow size, right? And equals to a constant. It's okay because they are used the same materials. They are used the same materials. Okay, and with the same geometric vector. Okay, therefore we can to figure out this failure stress of design B, this one, equals to 168 megapascal. So what's this result tell us? What this result tell us? What's the result tell us? For example, we design a crafted wing. We allow it has the largest flow size is 9 millimeter, and this wing will fail at the stress about 112 megapascal. Okay, if we allow the largest flow size of the wing is about 4 millimeter, and the stress to cause it fail is about 170 megapascal. Okay, so if I have a smaller flow size, that means have the higher failure stress. Okay, have the higher failure stress. Okay, so if we have doing some like a failure analysis, we can look at for example, we can observe, the aircraft wing while you have for example, you have the floor about like 6 millimeter. Well, so we can estimate what kind of failure stress is, right? And your spec of this aircraft wing is 9 millimeter. You will say, okay, it's fine, it's still safe, right? Because you define the largest fall size is 9 millimeter, but now it's just 6 millimeter, right? If your design is B and you observe the crack, it's about like 6 millimeter. Well, you will say, wow, it's already higher than the largest flow size that we already we define, right? We define. Therefore, we can say this aircraft wing needs to be repaired, okay, or needs to be strengthened by welding or different technique, okay, to strengthen this this aircraft wing. Okay, so it's totally based on what kind of the design. Okay, what kind of design we already mentioned previously, right? For the two different scenario, the maximum flow size or the design stress. Okay, design stress. So we are temporarily stop here. Next chapter, we're gonna focus on some like the ceramic crack and the ductile and brittle fracture from this some kind of the fracture surface. From this fracture surface, we have to estimate and we have to tell this kind of fracture belongs to ductile or brittle. Okay, so we're going to introduce this chapter next week. Okay, next week. So see you next week.